Okay, so here is the first problem. So I have a chain of length L, and it has a linear mass density lambda, and it's a height h above the floor on this frictionless table, and there's a tiny little bit hanging over, so when you let go, then it's going to just slide off the edge. Okay, so that's the situation we're going to deal with. So let's just go by the questions I wrote down before, and the first thing is, how many degrees of freedom? You could argue about this one for a while, but I think that we could all agree that there's only 1 degree of freedom. Because if you have one coordinate, you can tell exactly where that chain is. Let's pick this. Let's pick the height of the bottom of the chain above the floor as my 1 degree of freedom y. Okay, so that's easy. Next part, so we want to write down the Lagrangian. So the first thing is to get the kinetic energy in terms of other coordinates. Now, this isn't too hard, right? Because if this has a total mass of lambda times L, then I could say this is going to be moving in whatever direction, whether it's moving this way or that way. You know, at some point, here's my chain, and it's hanging over. Okay, so it's going down like that. But whatever the speed of this down is the same as the speed of that way. So if I just say the kinetic energy T is 1/2 lambda times L y dot squared, that's it, right? Because this tells me the speed of the chain. This is the kinetic energy. It doesn't matter that it's moving in the x or the y direction. You could break it up, okay? And it wouldn't be a bad thing for you to do. To say, okay, here's one mass and it's moving in the x direction, here's another mass moving in the y direction. They have, what's the relationship between those? How could I get x dot in terms of y dot? You'd find that they're the same. But you should do that just to check. So that's the kinetic energy. That's not too bad, okay? Now, the potential energy, that's a little more difficult because now I need to find, let's delete that. This is my variable y, and that's a length L. So how high is that above, how high is the center of mass of that above the floor? And let's break this into two parts. Let's say this is mg y1 plus mg y2, where this is y1 and this is y2. Okay, so y1 is the piece of chain hanging over the edge, and y2 is a piece on top. So y2 is just the same. It's just h. Okay, so I can just write that as h. But this is m1 and m2. This isn't the total mass. It's just the mass on the top, and this is the mass hanging over the end. But this is h. Okay. So how big of a piece is that right there? Well, if this total distance is h, then that piece right there is going to be h minus y. So the mass of m1 is going to be h minus y as a length times lambda. Now the height y1 is going to be in the middle right there, right? Because it's the middle of that thing. So it's going to be h. It's going to be the h plus y over 2. That's the average between this point and that point is in the middle. And that's where the center mass is. Okay, so I already have y2. M2 is just going to be equal to the leftover mass. So this is the length hanging over the end. It's going to be equal to L minus h plus y times lambda. This is the length minus the part hanging over the end, and that's my total length on the top times lambda gives me that. Okay, so now I get u equals, putting it all together, m1 is going to be lambda h minus y, g, y1 is just going to be this, h plus y over 2. And then I have this one, it's going to be equal to lambda L minus H plus Y times G times H. Okay, so I have my kinetic energy, that was easy. The potential energy was trickier